So in today's lesson, we're going to be discussing electric potential difference, which you more likely remember it as voltage. So this is a topic that you would have discussed in grade 9 science, but I want to revisit it today and extend it a little bit by quantifying some aspects of it. So electric potential difference, when it's introduced to grade 9 students, will often be described in by using an analogy, and the analogy is like the waterfall, right? So if you have like a cliff here, right, and you have water that's flowing over that cliff, if we talk about the water particles that are at the top, they have more gravitational potential energy than the particles at the bottom, but there's still that stored energy of these water particles at the top of the waterfall that can be utilized. And so there's a potential difference in a gravitational potential difference in those water molecules that allows it to be moved, or them to be moved from the top to the bottom. In the same way, we can talk about electric potential difference in the same way. So if we have an electric field, say for instance, right, so let's just say that, I have a positive terminal and a negative terminal, and we'll assume that these are little negative electrons. The amount of work that it would take to take that electron and keep it away from that positive charge, or to keep it from moving away in relation to this negative charge, we can talk about the amount of work that would be required to do that. Okay, so to move it from one reference point to another. Now that's one way to describe electric potential difference. So for example, this electron, or this charge right here, if I were to hold it, right, it has the potential to move towards the positive terminal. And so we can describe that in terms of how much work needs to be, how much energy per unit charge would be required to hold it away. Another way to think about it, and I kind of prefer this way of thinking about it, is that each of these individual electrons here will have its own little charge. And thinking about it this way is helpful when we start to analyze circuits. So this electron, and this electron, and this electron, and this electron, all these electrons are all part of the same current, right? But they might reach a junction where the current gets split. So let me just imagine, let's just picture this wire sort of splitting into two different pathways. So even though, these electrons are going to be split or divided, maybe two of them, maybe these guys right here are going to travel through this pathway, and these two are going to travel through this pathway, each individual charge keeps its same energy. The energy of each individual electron does not get diminished, even though the number of electrons might get divided into different pathways. So that idea is going to be important as we move through this unit. So again, the current describes the flow of the electrons, in other words, where they're going, but the potential difference describes the energy that each of these electrons can give to a particular load or area where the energy is to be used up. So now we can quantify that, right? Remember that I described voltage, or electric potential difference, as being the energy per unit charge. So I see energy divided by charge, so that makes sense. And also we described it as the work required to move it from one point to another in that electric field per unit charge. So just to remind you that, and I haven't included it here, and I definitely should. Okay, V is my electric potential difference, or voltage, and we measure that in volts, symbolized by the capital V. So work and energy are both units of energy, so measured in joules, as you would expect. And Q is measured in, is their charge, measured in coulombs, as we saw earlier. So let's do a quick unit analysis here to see how our derived unit relates to some of our other units that are used. So I know voltage, or electric potential difference, is measured in volts. So I'm going to use the symbol here, not in my formula, but thinking about the unit. And it's going to be equal to energy, or work, both of which are measured in joules. And I'm going to divide that by coulomb. So in essence, 1 volt is equal to 1 joule per coulomb. So here's another important idea that I want to remind you of from grade 9 science. So you'll remember the simple circuit here, and this is a schematic diagram. It's not a circuit diagram, which means that I've got the actual items sort of listed with not using any symbols. So, I know that in this simple circuit, my current is going to flow through the wires. The conductors in this case are wires. And so my battery here is going to provide the energy source for my load, which in this case is my light bulb. So that energy that passes through the light bulb, that's where my voltage is going to drop. I'm going to lose voltage. Why? Because the electrical energy that each charge in the current has is going to be given up and converted, transformed into into radiant energy and light energy to power that incandescent light bulb, right? So as an individual electron passes through this circuit, it's giving up all of its energy to that load, and then it needs to go back and refuel at my energy source. So really important for you to remember that, and that's going to come into play as we look at some circuit diagrams. So here's an introductory question that I would like for you to attempt in relation to potential difference. So it says 12-volt car battery supplies 1,000 coulombs of charge to the starting motor. How much energy is used to start the car? So give this a try on your own just to familiarize yourself with some of the new symbols and formulas that we've just learned. Pause the video now and resume when you're ready to take it up. Okay, so here is my solution to this problem. I'm given the voltage or the potential difference, and I'm given the number of charges, or sort of the charge in coulombs, and so I am asked to find energy. So I know that initially it would have 0 energy, and so in this form. So any change that I'm seeing is the energy used to power that motor. So using my equation, solving for delta E, remember that I need to get rid of this 1,000 coulombs, so I'm going to multiply by it on each side, and that gives me 1.2 times 10 to the power of 4 joules. So I'd like you to try this next example. We'll start out by writing out the givens together, but then I want you to pause the video and give it a try yourself. It's a little bit more complex, and we'll ask that you remember some concepts from our previous lesson on current. So the question reads, if a current of 1 times 10 to the 1 amperes takes 3.0 times 10 to the 2 seconds to boil a kettle of water, requiring 3.6 joules of heat energy, what is the potential difference across the kettle? All right, lots of data here. Let's start to write it out. So first of all, it's telling me my current is 10 amperes, so I'm going to write that out. The symbol for current is I, so my current is 1.0 times 10 to the power of 1. And I'm hoping that you're paying attention to the units, right? Not just leaving them out. Make a point of trying to remember what the units are associated with each dimension, because, of course, on any evaluation, you'll be expected to include them. It's telling me that it's taking 300 seconds, so that's a unit of time, so delta T is 3.0, bear with me here, this program is really slow, times 10 to the power of 2 seconds. What else do I know? And it's telling me that it requires 3.6 times 10 to the power of 5 joules of heat energy. So I can think of that as the change energy, or I can think of it as some of the work. Either way, it's fine. So my work is 3.6 times 10 to the power of 5 joules. And so what am I asked to find? I'm asked to find the potential difference. So potential difference, aka voltage, has the symbol V in our formula. So that is my required to find for this problem. All right, take a few minutes now that we've assessed some of the givens here about how to solve this question. Give it a whirl on your own. All right, so I've prettied up some of my solution here just to make it easier to understand. So where we left off was that we had our givens here. We were looking for our electric potential difference or voltage. And so really we had two equations to choose from. And I knew that I couldn't calculate the voltage directly because I didn't have my charge. And so I needed to use information about the current in order to solve for charge first. So that was my first step. So finding out the current by using, finding out the charge by using my current and my time data. Solving for Q gives me 3,000 coulombs. Just remember again that you're including your units, so double check that you included that unit of coulombs for your charge. Now I'm going to go ahead and I'm going to utilize that in my second step to solve for my unknown, which is my electric potential difference. And so I know that my work, my energy required to get the kettle going was the 3.6 times 10 to the power 5 joules divided by my newly calculated charge. And so when I look at that, my overall answer, plugging this value into my calculator, I'm getting 120. And that should make sense to you. The average outlet in your house, a normal general use outlet will have will supply 120 volts. So that should seem like a familiar and reasonable answer to you. So I'm going to just in a minute assign you some homework so that you can practice some of these calculations. Please see me if you are struggling with any aspect of this lesson. I'll be happy to help. So here are some suggested questions for you to enhance your understanding of these concepts. Remember that these, within these homework questions you will find some that they will ask you about information that is not in this lesson, but that will ask you to apply some of the information that we've discussed in this lesson. So make sure that you are thorough in your completion of these questions so that you can maximize your performance on any future evaluations. Good luck and see me if you have some difficulty.